Okay, welcome to Module 5 on black box testing, and this one will be an overview of black box testing, and then we'll go into a few more specific techniques in the next module. I'll also try to give some simple code examples in a follow-up video in Module 5. So let's get going. So yeah, a very basic backup to see what we're doing. So how testing basically works is we are going to write test cases. We're going to that somehow they will invoke the programs. It's a dynamic verification validation technique. So they will have specific setup for the program and inputs that we're going to provide. Then we get outputs from the program, some kind of summary of the behavior, typically outputs. And then we have some kind of oracle to guide us in knowing if the actual values we get back, the outputs we get back from the program we are testing, are the correct ones or not. So the test oracle doesn't care about the internals, the code, the structure, anything like that. The test oracle is about judging if the actual output from the program is correct or not. So we're going to compare the actual values that the program returns to the expected ones that we get from the oracle. So the test oracle is sort of the god. It knows exactly what should happen. So it knows the desired behavior for all given inputs. And of course, in practice, we will never have a perfect oracle. So we try to have as precise oracles as we can. And in the ideal case, I don't know if it's the ideal, but in an ideal world, we would have some kind of model or specification or a very, a complete set of examples that says what is the expected output for every input. But you can hear already, and we have discussed that before, that that's impossible because then we could use the oracle as the program. So in practice and in the typical case, the test oracle is a human, or it's a human that has some approximation of the perfect oracle in a model or in a specification or in a requirements document, right? So it's inherently impossible to have a perfect oracle for all inputs of your program, because then you could use that as the program, right? So if you have an executable oracle, which is complete, you could use that as a program. Of course, it could be too slow. There could be many reasons, right? So in some senses, you can approximate that perfect oracle, but in practice, this is not what will happen. Instead, you will have, for maybe parts of the software, there is a good specification. For other parts, you have to rely on your own experience and your own approximate understanding of the perfect case to act as an oracle. And in other cases, you might not know, so you sort of iterate between writing the program and deciding what should be the correct behavior. So yes, the problems I've alluded to here is that requirements might be described in a poor, non-testable way. They might not be complete. You might not understand them. Yeah. So wrong requirements or too approximate an oracle can lead to bad testing. It can lead to a low quality software and so on. So here you see the sort of general setting of where we are, but you see in this formulation that we don't really look into the box that is the program. And this is the big difference from the structural testing that we discussed in the previous module. So white box testing, right? There we look into the program and the software and we try to cover it, right? Here we look at this as a black box. So we're talking about black box testing from the outside. And the requirements is then in focus, the oracle. Terminology, general one, we discussed this already. Verification techniques can be static, like basically inspections, other forms of modeling that can help us prove things or judge things by reading them through, by sending them out to others and so on. Then dynamic verification techniques, the main one is different types of testing. And there we execute the code or we execute the model in some way. And when we execute the code, that is different types of testing. And we discussed white box, coverage-based testing. Now in black box, there are several techniques, right? Just to give a little bit of setting here, a test case consists of a clear description of tests to be performed. One test case is typically one or a very few things that we test after we have exercised or given input to the software. The idea with the test case specification, or the specification of writing down a one test case, is that it should be automatic, basically, to perform it. So a colleague of yours, if you're writing down test cases in textual form, it should be so specified so that if you give that to another engineer or a colleague that you're working with, they should be able to test the software, right? But most commonly nowadays, we write down test scripts in a certain testing framework, and then can be done by anyone. Just the computer will follow exactly the code and perform the test cases. But there are manual, scripted, and automated test cases. Manual ones, this is the tradition, especially for high-level system tests in industry. Then you have a textual description of steps, right? So you have like a name of the test case on top in the test case description. You have a purpose with the test case. For example, let's say we have worked with Saab. They develop air traffic control software, and then the name of a test case can be, check that system can handle 2 incoming aircraft at the same time, for different lanes or something like that. So this is the purpose, and then you describe it. You have like a date, a version, an author of this test case, and then come the setup steps. So this means boot up the system from a clean database, empty. Add these. The setup is add these 3 previous air flights or aircraft that have landed, that have already taxed and are in the airport, and then set up the airport with 3 different lanes according to these names and these lengths, and that is the setup, right? So the system is now in a state where it has an understanding of the airfield, the different lanes there. It has some previous data state about what happened before, and now starts the actual test case, which is we get information about 2 incoming aircraft from different directions. So then it says exactly in the manual test case description what you're supposed to do to test this case, right? So you have a number of steps. That is the actual test case. What is happening? What kind of input does the system get? And then in the end, it says expected output or checks, right? Or the checks can be inside the actual steps of the test case, or they can be at the end. And then you have something like, sometimes there's like a table, and every row has a case, a step of the test case, and then it says expected output. And sometimes they are empty, sometimes they are information saying check that in the list of ongoing flight on screen XYZ, make sure that 2 aircrafts are listed and that then one named Lufthansa 347 is on top because maybe it arrived earlier or something like that. So you have specific checks that you're supposed to check. So this is typically done not on the level of code units in the system or lower level subsystems. The manual test cases scripted like this are typically done on a fairly high level, like end users using the system, basically. Because it's very costly to write down, think of, and it's also costly to perform. So doing this on small subunits would be very, very costly. But, you know, this is the standard. So if you go to many, many companies, they will have system test cases like this, written manually in a big chunk of document listing many test cases. So I would say on the order of 50 to 100 is probably a minimum for a commercial system, and can go up a lot. Like I've told you before, some examples I've seen have been 10, 30, 50,000 test cases. But typically I would say, let's say in the range of 100 to 500 would probably not be uncommon, and higher for more complex and mature systems. Scripted test cases, on the other hand, is different from manual. So this is where we write code in some form, right? So executable descriptions that can be executed by computer, and typically used for lower level properties like unit test, integration test, subsystem test, and so on. So you can have the XUnit frameworks like JUnit, and they are available for C, CUnit, C++. All programming languages have that. It can be used. You can use scripts if you have more high-level things that maybe cannot be tested in one language. You can use Python, Ruby, Bash, Perl scripts to put things together and integrate things, sort of test integrated things. But they are readable for developers, right? So they can also serve as a type of documentation, although there's debate if this is good or not. Automated testing then is where you give some kind of model, so model of the inputs or model of the behavior, and when the computer executes this model to create the actual test cases, and then it runs it. So typically it can be based on some formal specification, but you know there can be levels of formality here, from very formal modeling down to very informal, more like random testing in a sense. So these are the main types and what you will find out there. Elements, fundamental components of a test case is what are the actions? What will you actually do to the system? What kind of inputs will you get? What are the steps? Then the expected outcomes, as I said. How should the system respond? They could be positive ones, is the most common. When I do this and that, the function call should return a 3, or hello world should be printed on the screen. Bad expected outcomes. Okay, this is when you write a bad expected outcomes, is when it's unclear, right? So if in a manually written test case, you say that, the expected number should be returned, but you don't say what is the expected number. It's not very useful for testing, right? But expected outcomes can also be of exceptions being raised and so on. So it doesn't have to be very precise, like this is exactly the value you should get back. And if the return value is very complex, let's say you're testing the generation of PDFs from Microsoft Word, it's not too easy to say this is exactly the PDF that should be produced. You get back a PDF and you will maybe check different things about the PDF you get back from Microsoft Word, right? You should check, is it the right number of pages? Does it have the right number of figures in the PDF? Is the date of when it was produced the correct one, the one that was the time when we called the output PDF function, and so on, right? So it might, your checks of the expected outcome might not be complete, as in this is exactly the binary file that I get back when I request a PDF. It can be about checking different things of the output, but not that the whole thing is exactly a certain binary file. Yeah, optional components, but this is something you see. There are standards for this that are used in industry. So you have identification, a purpose, as I discussed before, a reference to requirements. This is very common in industry. So for each test case, they are linked to requirements in the requirements document so that you can trace that for every requirement there is a test case, and for every test case there is some requirement that leads to it. Otherwise, why did you write the test case, right? They can be preconditions. This would be like things that have to be fulfilled before we can run the test case. So typically in the aircraft example would be that the database has been set up and is active. There's a certain number of elements in the database and so on. And initialization might be specific things we need to do before we can start running the test case, which are preconditions are the conditions typically after you've done the initialization. And there's much more if you go to the standard for this. But the important thing is to understand the fundamental components. We already said that. Here's an example of test case for a CD player. So we have an identification name or number called CDP volume 1. The purpose is to check the volume control. The precondition is that some music is playing and you can hear it in the speakers. So this is a manual test case, of course. It will be hard for a computer to check this maybe. So step 1, action A is turn volume control in both directions. So you can see this is a test case for a human, for a manual test case. The expected outcome is that turning the volume control clockwise, so to the right, in the same way that in a manual clock, increases the volume of the music, and then counterclockwise to the left decreases the volume, right? So it's fairly unclear here. It's not exactly how much should it go up and down, but it's usable for a human to check this, right? Action B, the next step in the test case is turn the volume control counterclockwise as far as possible, right? So there's a stop on the volume control. The expected outcome is that the music playback is completely silent at the stop, right? Makes sense. Action C, turn the volume control slightly clockwise. Okay, so take it from the stop, I guess, but this is a bit unclear. But if we are doing the action next from action B, it would be to turn it up a little bit. The expected outcome is that music is audible within 3 millimeters of silent position. So it's here you see it's a little bit imprecise. What does it mean 3 millimeters? Where should we measure that from the silent position, right? Is it on the rim of this? Is it somewhere else, right? Should you measure it along the circle or in some other way? So you can see here that typically for humans it would be enough to have this type of imprecision, but you know, when you have more complex test cases, more complex systems, this can lead to different testers using the same test case specification in a different way, and that might not be good, right? Because we're testing different things at different times. Test cases and specifications. A test case verifies fulfillment of some particular aspect of the specification. Yes, this is obvious. So one test case will test some requirements, not the whole thing. Test cases are usually derived from the specification. So we're talking about black box testing here, right? So we're not looking at the inside. Coverage techniques can help to direct the focus. So coverage here means requirements or specification coverage, right? You remember at the end of the structural white box testing module, we talked about coverage. And there we discussed coverage, of course, inside the box, right? White box. So coverage of the code structure or some graph or some logical expression that is relevant for the implementation. Coverage on the black box level means coverage of the specification. So, for example, if you are tracing from the requirements to test cases, coverage means that the requirements that have so far not been covered at all or have only been covered by a few test cases are the ones where we're going to add test cases, right? So we're using the specification coverage or requirements coverage to direct what next, because maybe we have an expectation from the user or customer that we are going to have test cases for every requirement in the specification. But of course, in the end, a collection of test cases, what is often called a test set or a test suite, which a test suite is typically a larger set or multiple sets merged into one of test cases, is not a specification. I mean, we are trying to come up with concrete test cases for the requirement or for the specification, but in some sense, they are only samples. They're only specific cases that a specification is a more general description. So, you know, there's much debate about this. Some people say, oh, we can just write test cases. Others say, just writing test cases is not a specification per se. And of course, they are not the same, right? And they can be good or bad, both of them. A test suite or a test set which have very few test cases is not going to be great. But also a specification that is very imprecise or incomplete, so it doesn't cover all of the behavior, is also not going to be very great. So there's like, but they are not the same thing. One is a different way to express some of the parts of the other one. So what can we talk about software specification here? What is, well, the specification is what is the software supposed to do? So it's a way to express the oracle, right? What should really be happening, not what is actually happening. What is actually happening depends on our implementation, but the specification is about what is supposed to happen, what should happen. And here the traditional view is that we talk about two main types of properties. So functional properties. They are specific behavior of the system. What should happen when we do this? This should happen, right? And then non-functional are all the other stuff that is important, but it's not captured in the function themselves. So performance, right? How quickly something happens can be very important to a user, but it's not part of the functional property. I mean, something which is very slow, but let's say you want to print a PDF, then part of the functional properties, the functional specification of Microsoft Word is that if I select the export as PDF function, I can find a PDF in this in the chosen directory of your hard disk, right? This would be a functional property, but the non-functional properties attached to that is if a requirement says this should happen within 1 minute of invoking the export to PDF function. That is a performance requirement. It should be at least it should happen within 1 minute. So it's a non-functional property. Usability can be another one. So the way we present, the way you're supposed to select the function is about the usability. It's not about the function itself. Function is just that it can do a certain thing. The non-functional properties are about how well it's done in a sense, in some other aspect, right? Does the code follow the coding standard? This is more of a white box non-functional property. That the license is of a certain type, that we fulfill certain, that we've used certain standards. This can be part of the non-functional specification, but it's not about the specific functions of the software. So you probably know this from other courses. Okay, there are different kinds of specifications. Obviously, informal ones is the most common. So you have descriptive text, like requirements in natural language. This is by far the most common. Then you have semi-formal, so here you try to structure in some kind of models what the software is supposed to do. And often this can be UML diagrams, so like use case diagrams, state diagrams that capture somehow parts of the behavior of the software. It can be more specific interaction diagrams, so like sequences. When we do this from the outside, the system should return this and that in this sequence. Communication diagrams can be used and so on. And then, of course, there are formal specifications. So here you describe in more mathematical or precise or exact form what should be happening. So typically the traditional here is state machine models, and you will hear more about this in the model-based testing modules coming later, like finite state machines, extended finite state machines. So different types of modeling ways to model that can help you be exact in what should happen, in what order, what should be exactly the output given the input and so on. Algebraic specifications, they are equations, more like using the logical expressions to relate different functions to each other. So one example can be an algebraic specification of a queue in the data structure, a queue, right? Can be that the number of elements in the queue at any time should be the number of elements that you have added minus the number of elements that you have taken away, right? So the number of added minus the number of removed should be the number of elements currently in the queue. So this can be expressed in a logical equation that relates the state and actions of what has happened to the queue. You can use more advanced logics or formalism like temporal logics, where you also model times. You can say what happens before and after other things, or in different time intervals and so on. So, of course, black box testing, there are many, many ways. We're not going to talk about all of them in this course, and especially not in this module, but we're going to talk about random testing, such a basic one, and also heuristics for deriving black box test cases, which is more based on experience from good testers in the industry. But then there are more, say, systematic techniques like equivalence class partitioning, boundary value analysis, and some of them we will discuss in the coming modules, but we will not cover all of them in the course. Error guessing is more heuristic based. Use case testing is more driven by UML diagrams like use case diagrams and so on. So there are many, many black box testing techniques, and what they have in common is the initial structure, that we don't look inside, we look at some approximation of the perfect oracle. So we look at the specification or based on our experience, and then we write down test cases from the outside. So the traditional view is, as we've seen before, is that black box testing is, a black box. We give input and we get certain output. But of course, in reality, this might be too simple a view. This view suggests that we can just have a series of inputs and we can describe the output. But often, of course, the software itself has some kind of state. And then the expected output will depend on the inputs that we've given in before. So it depends on the history of what we did to this piece of software before, right? So to give an example, here you have a case where a general case where it doesn't have a state. So here you're giving inputs on top, and the software here as a black box is giving some output, and here there are 5 test cases, and somehow here it seems to be the identity function. So it's just giving back as output what it got as input. So this could be, but it can be like this for many other functions, that it basically doesn't have any state, but when it has a state, then you have to take that into consideration. So here we first gave 24 as input, and we got 24 as output. Then we gave 24 again, and we got 24 as output. But then when we give 20, it's apparently giving 22 as output, and 21, 20.5, and so on. So actually what is happening here is that the software is returning the average temperature over today and yesterday. So, you know, we have to take the sequence of inputs into account to see, to know what is the oracle, the expected output, right? So this means that before we can execute a test case, we have to bring it to a known state. And then we should try to cover as many states as possible. So that's a general target here of in black box testing. We want the software to be in as many different states as possible to cover the possible scenarios that it can come into when it goes live. Okay, so how do we, so this was the point there was that you sometimes, and very likely in reality, you have to consider the state, right? But functional programming languages, for example, they try to take away the state as much as possible so that the functions are pure, so you can actually test them in isolation like this. And this is also something that you have to think about in reality when writing test cases, that if the test cases depend on the state and you haven't explicitly written that in the test case, the order in which you run the test cases might affect if they pass or not, even though the software is correct. So this can be problematic. So basically you try to write test cases in the ideal case that can go from a blank slate, setting up the test case and then do the actions and check the outputs. But often for complex systems, it's too expensive to set up a new system and set up the databases and whatnot. So then you have to consider the state. So how do you do this? Well, you look at the specification, whatever form it has, and you try to come up with test cases. You're generating test cases from your understanding from the specification. So you can enumerate statements in the specifications, like if there are individual requirements, like we said, try to cover them. You can have models of the behavior. So for parts of the specification, you can have a more formal model, like a finite state machine. You can go through use cases and you can sort of translate them into test cases. So use cases are often like an abstract description of what should happen. And then you can, by filling in specific inputs, you can then create multiple test cases from one use case. But then there are, of course, techniques that more systematically can help you create test cases. So equivalence class partitioning is about finding different typical classes in the input space where the behavior of the software should be similar. And then when you know about these classes where the behavior is equivalent for inputs in that class, then you try to write test cases for as many of the classes that you've identified as possible. And finite state machines can help in that, but there are also other ways to do it. Boundary values, we will talk more about this in a later module, but basically instead of looking at the general classes of inputs or states, you're looking at the boundary between two classes, right? So, you know, maybe there you have the specification is saying what happens for the positive inputs values and for negative input values. And then you also want to consider values around 0. So 0, 1, +1, and -1 are very interesting boundary values. But we're going to talk more about this because this is something that we do in our research group. So I can summarize one of our later papers on this in a later module. Error guessing is basically heuristic. You know, based on your experience, you try to guess what are the difficult cases. Are there values that seem to be especially dangerous or hard to handle or are on the boundary between different things? And then random testing can be a great black box testing technique. So you write general test cases. You say that the precondition is the account contains a certain number of crowns, M, which is, and you have a value N, you select then a value N, which is smaller than the amount in the account. Then you take the action in this test case that you withdraw N. So you're now withdrawing N Swedish crowns from the account that has M, which is the same as or larger than N. And the expected outcome is now that the new balance in the account is m minus n. So you can generate random sequences of test cases from this by basically sampling integer numbers m and n and ensuring they fulfill the precondition, right? Yes, and when you do this, of course, you can be smart about it. So try to create sequences that make sense, right? So if you just do random numbers here, you will not fulfill the preconditions. So I can show a little bit later in an example. So how do you identify characteristics of the software and of the input space? So if it's functionality based, then you try to identify intended functionality of the system. So you need to domain knowledge. What do we know about this domain? If it's finance, you need to understand accounts, interests, you know, how the interest rate of the bank is affected by the interest rate on the Swedish national bank and so on. So you need often a lot of deep insight into the domain to understand the intended functionality, so you have good knowledge of that functionality, and then you can start being an oracle or describing what are the expected results when you run the software. So writing requirements that are testable can be helpful. There in the requirements engineering course, you've seen probably examples of this. How do you write requirements so that they are easier to understand and thus to write test cases from? But in reality, for complex systems, your requirements are incomplete. And then it can be hard, so you have to be inventive and creative when you create test cases from that. And requirements are often abstract, so it's not often easy to come up with good input parameters from abstract requirements. An example requirement can be there should be a function for drawing a triangle. Okay, but it has, you know, triangles look very different depending on how they are constituted. So equilateral ones have all the sides of a triangle have the same length, so they are very symmetric. Isosceles triangles have two sides being equal, while the other one can be any length, basically, to be a valid triangle. And then scalene triangles have non-equal lengths of the triangle. So, you know, the requirement didn't say something about these different classes, right? So you would have to know about triangles to understand that you need to test the drawing of triangles will be quite different for these different types of triangles. Another way is to do interface based. So then you go probably not only from the requirements, but often there's an architecture description or an API description or a high level design or even a low level detailed design. And then you can look at the interfaces of these components. So you identify classes of inputs from the interface description. So what are the data types? How many arguments are there? And so you look at the method signature and the fields in there, and you try to go from there. This is often easier to apply, and you can directly get executable test cases, but you don't have a very specific oracle, maybe, because you don't. It's only the API, so you don't know exactly what kind of output to expect. But often you have your knowledge about the requirements and combine that with the interface knowledge and the information, and then you can come up with values. Of course, at this level, you need to consider combinations of values, and we will talk about that in the coming module. So an example here would be for the function for drawing triangles, you would just treat the three values as integers. And maybe 0 is a special value. So the three parameters are the length of the sides, and you wouldn't really know what are different types of triangles. At the interface level, you just see that the draw triangle function has three integers. You would write test cases based on that, right? You would probably understand that 0 is an interesting side case, so we should try that and so on. Okay, to wrap up about black box testing, that in practice, what happens, right? What happens when you're doing black box testing? What happens is that you as a tester, you use your previous knowledge, your experience, and then it's kind of a heuristic base, so it's not so systematic. Many companies, they apply systematic black box testing, so they have a specific technique, and we'll talk more about those in coming modules. But there's always heuristic knowledge being used, and there are, specific proposal like this one called the right bicep method that can help guide you when you're not so experienced, right? So these are summaries that have been written down by experienced testers on how do you come up with test cases, right? And this specific summary is called the right bicep. It comes from Andy Hunt and Dave Thomas' great book, a classic called Pragmatic Unit Testing. And it's available for many languages. So this is a very practical and hands-on book to help you become a better tester. And they give this right bicep as a sort of high-level heuristics, how you create good test cases. So of course the so bicep is an acronym basically, and the right is so important. So it's not called R bicep, it's called right bicep, because right is the primary thing. Do you get the correct result when you invoke a function or a subsystem of the system? Well, okay, so here you can see that the right embodies understanding of the specification, so it doesn't really help you. But of course, as a human, you have some knowledge of the specification. So they have this as this first step in this heuristic method, in this guidance to you. The B in bicep captures boundary value testing. So are all the boundary conditions correct? So you test now things that are on the boundary cases of the behavior. So what happens if you give 0, right? What happens if you give a very large value and stuff like that. The I in bicep means, can we check inverse relationships? So this means, for example, if we have a queue, if we first add one element and then we take out one element, it should be the same element, and the length of the queue after that should be the same as it was before. So this is an inverse relationship. You first do one action, then you do the inverse action, and you check now you know that the state of the software after these inverse actions should be similar to what it was before. So it's a general technique to create test cases that is, think about, are there inverse relationships? And it doesn't need to be simple as add and delete. It can be different things, right? It can be more complex things. So it can be things like if you have an AI or machine learning component which takes images and it gives a summary of the image. Say you give it a picture of a cat and it says cat, right? An inverse relationship here might be something like that. If you make a very small change to the image, you expect it to still say cat in a sense. So you're somehow relating here. Maybe this was not an inverse in particular, but you're relating two actions or multiple actions to each other. But the I in bicep is specifically about inverse actions or relationships. The C is, can we cross-check result or using other means? So the typical here is something called differential testing. And this is very common. For example, if you're testing a piece of software in different versions, so you're developing the software, then you want to do differential testing from today's version to yesterday's. So if you every day when you test the software, save some data for random inputs. So you generate random inputs, you save what was the input and what was the output. today, then tomorrow we can use this to cross-check that it hasn't changed. And maybe it should change for some of this data, but differential testing means to differentiate, compare two different ways of getting the result. So you can do it in versions of the same software. You can also do it comparing this software that you're testing to some other competitor software, an open source system that is supposed to do the same or a similar thing to what you're trying to do, right? So cross-checking the results using other means. The E in BICEP in this heuristic means, can we enforce error conditions to happen? So E means think about the errors, right? What should happen if you're trying to create a PDF from an empty document, right? Should there be an error or maybe not? Okay. So in that case, we couldn't come up with a test case, but we're thinking like this. We're saying what happens if we're trying to let's say change the rows in a table, and then you're at the maximum number of rows, or for example the table is already filling one page. So what happens if you now add a row? Maybe it should become an error in that case, or how should it be handled? So you're thinking about specific error situations in the E. And then P, they consider performance such an important non-functional criteria or property of the system, so they lift it into this. So you can see that this is incomplete, the right BICEP heuristic, but it's something that they've learned through developing software throughout many, many years. This is a very good sort of high-level heuristic method to derive black box tests. Okay. If code ran correctly, how would we know, right? So it's about collecting to the specification. The boundaries are what else can go wrong at the boundaries between different inputs. Logical inverse. I mean, if you can find very clean inverse relationships like add and delete, then you look at the state before and after and compare them. Is an alternative algorithm, even if you cannot find a competitor or an open source or some previous old version of the system, maybe there's a simpler algorithm to do what you're doing that you can compare in some of the inputs, even if it's not for everything, right? And then error conditions, and are there other non-functional requirements than performance that we can? So this is a way to extend the P in right BICEP, right? Efficiency, I mean, memory use can be another thing to performance, or usability can also be something that we consider here. Okay, so the right BICEP, here are some further examples. I think we've already discussed that, but you can check it in the slides. Boundaries, and then their book goes into specifics. So right BICEP is a high level guidance, and then for each of the ones the book goes into more detail. And for boundaries, you can look into an acronym called CORRECT, which means how do you check things at the boundaries. So conformance, does the value conform to an expected format? Ordering, is the set of values ordered or unordered as appropriate? So this can help you actually go into more specific ideas. Okay, so that was an overview of black box testing. I will give some code example, and then in the next module we'll go into some more systematic ways to do black box testing. Thank you very much.